This video covers mutually exclusive events where there is no overlap, and then later we'll see about inclusive events where there's some overlap between A and B. So a mutually exclusive event is a simple event and it describes a single outcome. Now, a compound event is made up of two or more of these simple events, and when we say mutually exclusive, that means that the events cannot both occur in the same trial. So this is the formula for it. And we realize that the U without the tail to the right is the symbol for union, and it is simply going to be the probability of event A occurring plus the probability of event B occurring. Let's take a look at an example. A group of students is donating blood during a blood drive. A student has a 9/20th probability of having type O blood and a 2 out of 5 probability of having type A blood. Now, we need to realize why this problem context is for a mutually exclusive event. You cannot have two types of blood. And for that reason, when we answer the question, what is the probability that a student has type O or type A blood, we will use simple addition of the probabilities of those events, which gives us the following formula. And then the probability of type O is given as 9/20ths, and for type A is given as 2/5. After making common denominators, we get the following result of 17/20ths. Remember that mutually exclusive events is simply the sum of the probabilities of each of those events occurring. You don't need to worry about overlap. Inclusive events, on the other hand, do have one or more outcomes in common. Therefore, you must subtract the overlap of the two events. So then, that prevents those outcomes from being counted twice. So if you have event A, it's overlapped with event B. So when you add A with B, you're counting the elements in here underneath as part A, and over here on top, part B. They're counted twice, but you only need to count them once. And so we still look at the probability of A or B occurring as the probability of A occurring plus the probability of B occurring minus their overlap, where this is the AND symbol. On a number cube, finding the probability of rolling a 4 or an even number needs to strike us as inclusive events because 4 is an even number. So the probability formula is the probability of rolling a 4 or an even number is the probability of rolling a 4 plus the probability of rolling an even number minus the probability of rolling a 4 and an even number. So down here we could see that on the 6 sides of a number cube, we have the numbers 2, 4, and 6 are even, and so 4 would be counted twice, so we need to subtract that out. To find probability, you do favorable over possible. Favorable is the number of 4s on a 6-sided number cube, which is just 1, over total possible, there are 6 sides, plus the probability of rolling an even, so 1, 2, 3 out of 6, minus the number of 4s on the number cube, which is just 1 of those 6 sides, and so then those subtract out, and you're just left with 1/2. Now we're to find the probability of rolling an odd number or a number greater than 2 on a 6-sided number cube. So the diagram here shows that the odd numbers are 1, 3, and 5, and we could see that 3 and 5 are numbers that are greater than 2, so these are inclusive events. So we get the following formula. So here I'm showing that I take the simple event, probability of an odd, plus the simple event, probability rolling a number greater than 2, and then because these are inclusive events, I have to subtract their overlap. Substituting in the numbers, you get the following. So notice half of the numbers on the 6-sided number cube are odd, and then 4 of those 6 numbers are greater than 2, and of the numbers that are greater than 2, 2 of them are odd. So then we have a 5/6 chance of rolling an odd number or a number greater than 2 using a single number cube. This should make sense when you think about it in terms of the complement, because I could just ask what's the probability of rolling a 1, and then that would be 1 minus 5/6 or a 1/6 chance. The next two problems increase in difficulty. So the first example asks us to find the probability that a student was a senior or read a daily paper. We're given that 1,560 students were surveyed, 840 of them were seniors, and 630 read a daily paper. Only 215 of the paper readers were juniors. Now, the wording is tricky. The problem does not mention anything about underclassmen, so we will not consider them in the survey. We get the following formula. So we want the probability of selecting a senior or someone who was surveyed who reads the newspaper. Now, we have some seniors who also read the newspaper. So that's why this is an example of inclusive events. So we add the probability of pulling out a senior from the survey, pulling out the probability of someone who reads, and then the probability that they do both, that they're a senior and they read the daily paper. Now, you have to be careful. This 630 does not refer to the seniors. That is of the students surveyed. This here is like the subject of the sentence. Filling in, we get the following numbers. There are 840 seniors out of the 1,560 students surveyed, plus there were 630 readers out of all those surveyed, and then minus, now we're only told about 215 of the paper readers were juniors, so then the complement of that, so 630 minus 215 is going to be the number of seniors who also read the paper. So we get the probability of selecting a senior or a paper reader is 67.6%. The last example requires us to be smart in our use of the complement. Consider directly calculating the probability that at least 2 students choose the same butterfly out of 6 students from a list of 8 butterfly types. So that would mean we would need to find the probability of 2 students choosing the same butterfly, plus the probability of 3 students choosing the same butterfly, plus the probability of 4, 5, 6, 7, and, all the way up to the probability of all 6 students choosing the same butterfly. That is a lot to calculate. So rather, I would find the probability that all students choose a different butterfly and subtract that from 1. Using the complement is going to be a lot easier to then find the answer that we're trying to get. So the probability that at least 2 students choose the same type of butterfly from a list of 8 will equal 1 minus the probability that all students choose differently. This is known as the complement and gives the following. Let's unpack this probability. Looking in the numerator, it defines the number of favorable outcomes. It's a permutation, first of all, because objects may not be repeated. You can't choose the same butterfly. So therefore, the first student has 8 choices. The second student, 1 fewer or 7 choices. All the way down, and so that is going to be represented by 8 pick 6. The denominator is the sample space, the total possible ways that 6 students can choose a butterfly from a list of 8 types. So if objects are repeatable, then the total possible is going to be, well, the first student can choose 8 butterflies from among 8 butterflies. The next student, because objects can be repeated, also has 8 choices. All the way down the line, so that's 8 to the 6th power. And this gives us a probability of 92.31%. Developing an intuition of when to use the complement is very important in solving probability problems. What you need to look out for is whenever you're asked to find a lot of different probabilities, think about the complement as a back door. So instead of individually calculating 2, 3, 4, all the way up through all 6 students choosing the same butterfly, we said I could reword this by saying that's the probability of all of them choosing differently. That would define the complement, so then I could subtract that probability from 1.